Okay, well, first of all, thank you to the organisers and particularly to Michael Heller for the invitation to be here with you today, which was a slightly unexpected invitation. You might like to think of this talk as the interlude between the profundities that we've heard in George's introduction and the hard stuff that's going to follow after the tea break. I'm going to start off with awards nominations. And my nominations are for the causes of the First World War. These are all taken from scholarly articles and books seriously proposed as what caused the First World War. And there are various categories. I'm not going to read them all out, you'll be pleased to know, because you will get the point before I get to the end. There's only one nomination in the individual category, the one that we all know. Various countries have been nominated for the cause of the First World War. Austro-Hungary, France gets 1 nomination, Germany gets 4 nominations, Britain gets a nomination. One of those German nominations, those are well known in Britain, the railway timetables cause of the First World War. And down at the bottom there, the British diplomatic bumbling in Europe, which we're probably all very familiar with. Then there's joint awards. Countries together, quite like the last one of those, all participants more or less equally. There's group awards, for example, the German military leadership there. And then apparently abstract ideas can also be causes of the First World War. So basically speaking, the first two, the whole of history was what caused the First World War. And then apparently abstract ideas as well. So imperialism, nationalism, social Darwinism, and so on. What's the point of this? Well, you've all by now got to the point, which is that in a complex system, identifying causes is, if you like, a lost cause. If we have a linear system, then the mapping between causes and effects is straightforward. If we have a non-linear system, then the effects feed back into the causes, and identifying cause and effect becomes much more problematic. What we try and do, therefore, and what all of these scholarly articles have tried to do, is to identify what one might call perturbative causality. That is to say, how small changes in causes have produced small, or as we'll see, large changes in effects. Demonstrate my ability to read Polish. Okay, so let's take a famous example. Well-known example in the sociology, economics literature is the regeneration of Times Square in New York. And there, the Times Square was very run down and was full of undesirables, sleaze, drugs, and so on, until Disney decided to open a cinema there. And then everyone saw that people were visiting the cinema, there was money to be made, and the drugs and sleaze was cleared out, and Times Square is now a much nicer place to visit. That's the urban myth, identifying one cause there as a tipping point, a delta cause producing a large change. If you actually look at the history, there's a lot more complexity underlying even this simple, well-known example. So let's go to something that George mentioned, reaction diffusion equations, where we think we can have a little bit more success in identifying perturbative causes. And here we've got two reactants, C1 and C2, an activator and an inhibitor, and the activator diffuses more slowly than the inhibitor, and the result is an emergent property that is unpredictable from just the from the statement of the equations, from the statement of the context. What we have are all these gorgeous animal patterns as a result of the mutual interactions of these chemicals. The important point is that it's the situation in which these materials find themselves, in which this inhibitor and activator find themselves. It's the way they interact that produces this emergent behavior. So it's the agents and the way they interact that leads to emergent behavior. Here's the well-known example of emergent behavior, the ISEE model of magnetism. On your right there is a square grid, which you can imagine the light blue patches are little atomic magnets pointing in one direction, let's say up. The dark blue patches there are little atomic magnets pointing down. And those magnets like to align, so they would all like to point in the same direction. But we've embedded this system in a finite temperature environment, which means that there are fluctuations, thermal fluctuations, which means the magnets can flip. And so there's a balance between the desire of the magnets to align and the thermal fluctuations which are forcing them to flip. And we can actually have a look at what happens here, if this behaves as predicted. So, here is a random setup of positive and negative upward pointing, downward pointing magnets. And if I choose the temperature correctly, these will flip around until you get large patches of magnetism in an up direction, large patches of magnetism in a down direction, until eventually the system will flip one way or the other. It takes a long time. I'm not going to leave it running for long enough, but it will eventually flip one way or the other. But it is not possible to predict which way that system will go. Let me stop this. It actually looks as if it's going to go negative. Let's show you the result of a run there in the center of that picture. You'll notice that run was rather longer than we've got time for. There are 8 million time steps in that run. And what we see at the beginning is that the magnetization has flipped downwards, and it stays down for a very long time. And then, for no apparent external cause, but just because there are fluctuations in the system, it fluctuates upwards. So this is a system where the interactions are all perfectly well defined. It's very simple magnets. And there's a thermal environment, but it's at a point where the outcome is entirely determined by fluctuation. So I don't think you have to go to the quantum level to get unpredictability. You have to go to a system that is exhibiting critical behavior at a critical point, and we can get these random fluctuations. So if you appoint your senior, where's the mouse gone? You appoint your senior CEO at this point in your company's downward fortunes, and the company flips upwards there, the CEO will, of course, claim enormous rewards, but it may well simply be a fluctuation in the system. Okay, on the bottom right there, we've got something, again, George alluded to, the behavior of hydrogen in water, the behavior of water molecules in water. The properties of water are not determined by the individual molecules. Viscosity is not a property of the individual molecule, it's a property of the interactions between those agents, between those molecules. I've got a few more examples before we get to the cosmology. A couple more. This is a game or computer program called Angels and Mortals. What we have here is a landscape populated by a cloud of mortals. Each of these patches, the white patches, are mortals, and they diffuse at a certain rate. And then we add some angels with a certain density, which they can diffuse at a certain rate. And then at each time step, a fraction of the mortals die. And if there's an angel on a patch, the mortals multiply by a certain factor. If you use a mean field approach to this, you can set up a differential equation, and you can predict exponential decay under certain conditions. We actually look at what happens here. If we actually look at what happens there, what we see is that in fact the mortals don't die out, but local fluctuations dominate the system, and the overall predictability of the differential equation is not actually describing the system as it is. And then I've got one more of these that I want to share with you, which is one of the most famous examples of applications of these simple models in sociology, the Schelling segregation model. The idea here is that you look at two populations. For the sake of argument, we'll call them red people and green people. And you observe on the right there that somehow the population is segregated. The green people live in green patches and the red people live in red patches. You might deduce from that that there's a certain amount of colour prejudice here. Red doesn't like a green but likes red, and green doesn't like red but likes green. What Schelling showed is that you can get this segregation in situations where there is, in fact, only a mild preference for being near a neighbour of your own colour here. So let's just run this one. Yeah, let's do it. So we'll just set this up. That's a random distribution on the right there of greens and reds, and this actually goes rather quickly into patches of green and red. The conditions under which that's happened is that there is a 1 in 3 preference to be near someone of your neighbour of your own colour. So this situation is one in which we can't argue from the observation to the microstructure of what is causing this. Now, let's come and look at the aspects that may be relevant to cosmology. What I want to look at is the idea that there are certain requirements, very stringent requirements, on the constants that make up our universe that are necessary in order, not that life as we know it exists, we know there are going to be stringent requirements there, but that some sort of intelligent adaptive systems might actually emerge. And these are the conditions under which the universe is supposed to be complicated enough for that to happen and long-lived enough. There are many different people who have written about this. I happen to have taken the constants from Martin Rees's book. He's got 6. I'll just mention 4 of them here. The strength of gravity, the ratio of the strength of gravity to the electromagnetic force, 10 to the 38, or 10 to the minus 38, controls the size of the universe, gives us enough room for galaxies, stars and planets to form. The critical density, the amount of matter that there is around, controls the length of time that the universe exists for, so it can last long enough for the development of complex life. Nuclear binding, which I will come back to, which allows stars and element formation, and then the ratio of gravitational binding energy in large structures to their rest mass energy, or equivalently the size of fluctuations in the early universe, which dictates the possibility of formation of large-scale structures rather than nothing very much, or all the matter going into black holes. So that appears to need a very large degree of fine-tuning in order that complex structures, such as the galaxies, stars, planets, life, and us, can emerge. What I want to argue is that one can view the emergence of complex structure in a number of ways that makes it much more likely that complex structures emerge under a variety of conditions, and that the fine-tuning argument is probably not yet settled. Let me put it as weakly as that. Here's one example. The existence of metabolic networks. The pattern behind the slide is a chart of metabolic networks in a typical cell. The foreground shows an attempt to create an artificial metabolic network with an abstract food set and interactions whereby each of the steps in that network is catalyzed by a product itself made within that network. That sounds like a hugely engineered undertaking. Our cells have managed, by the processes that George talked about, to engineer themselves to achieve this. But in fact, Kaufman would argue, if you look at the mathematics, if you have a large enough food set with enough basic interactions, then this sort of thing, this level of complexity emerges automatically. Here's another example of a hypercycle, so-called hypercycle, in which there's an intricate arrangement of molecules producing enzymes, molecules here producing enzymes which catalyze the formation of molecules which produce enzymes, which catalyze the formation of molecules which produce enzymes round a so-called hypercycle. You might think that this is highly engineered and that this sort of entity, which is one of the possible approaches to the origin of life, to molecular evolution at the beginning of life, might be rather difficult, that you might have to tune everything to get something like this to emerge. Well, this is a very, very simple example. I don't want to go into the details of how this sort of entity evolves without fine-tuning. And just to simplify this picture, what we have here is an entity which, for the sake of argument, we'll call a cell, with a green boundary. So I can't point at the thing and talk into the microphone at the same time. Can you hear me at the back okay when I'm down here? No? Okay. Right, I'll wave my hand at it. You notice the top left there, we have a cell with a green boundary and a red boundary. The green boundary produces red molecules that form the red boundary. the red boundary produces green molecules that form the green boundary. When that cell splits, the information to reconstruct it is present in each half of the cell. So at the top on the right, the red boundary reconstructs the green boundary, and at the bottom, the green boundary constructs the red boundary. So this is an entity which can reconstruct itself, and which will therefore take over in any number of these, in any environment in which these entities are allowed to multiply. So, now, the example I'm going to show you, none of the constants have been engineered. There's a large number of molecules. They're assigned random catalytic properties. They're assigned random properties which get them to associate into either the green boundary or the red boundary. And what's going to happen is that we're going to see we're going to see on the, if you just concentrate on the graph that's off to the very far right there, what we're going to see is that a very large number of types of different entities with these random catalytic properties and these random properties of assortment are going to grow such that some of these molecules are going to begin to dominate. Some of these entities are going to dominate, and in fact, if I let this run, which is doing rather slowly at the moment, you can just begin to see some peaks poking up there, which are the beginnings of this hypercycle taking over. And let's stop it and show you the result of an earlier run there on the right, where you see there are three peaks there, the main one and the two side ones, which represent a hypercycle that's emerged from this system without any special tuning. Okay, now this is unpublished work, so I'm not going to make a statement about how the balance of when you actually get hypercycles emerging from randomness and when you don't, but the tests that we've run so far suggests that the emergence of hypercycles like this is a characteristic feature of this system, provided you have a large enough set of molecules to begin with. I'm going to put this into some brief mathematical context. There are attempts to model this sort of behavior, in particular Stuart Kauffman's so-called NK model, which is now widely used in physics as well as ecology and economics. Basically speaking, we have a mapping from genotype to phenotype. The genotype contains various alleles, which we can call 0 or 1, 1, 2, 3, or 4, or U, G, C, and T, if you like. But the phenotype, each characteristic, each trait, is determined not by one of the genes, not by one of the possible alleles, but by the alleles interacting, by the genes interacting. So there you see that there are actually 3 genes that interact to produce the trait in the phenotype. So that's there are 8 of those genes, so that's n equals 8, and each gene depends upon its 2 neighbours as to what trait it produces, so k is equal to 2. Here you can assign arbitrary fitness values to each of those interacting genes, and you can calculate therefore the random sum of the effects of neighbouring genes, so the contribution of the neighbouring genes to the fitness of the phenotype, the particular trait. And you can plot the landscape of fitness against genotype. And that's what we get. That's what we get in the next slide, down the left-hand side, what we see is that in general, a complex landscape emerges. And these are the adaptive landscapes that, again, George was talking about, where we have systems that climb to the top of those fitness peaks by adaptation to their environment. The point here is that the complexity arises from very simple underlying rules, just as they did in the ISEE model that we saw. And then one final thing that I'd like to show you, the NK model applied in an economic context. I won't run this one, I'll just say what the result is. Again, it's stuff that we haven't published yet, but what we're looking at is firms, the coloured dots in the picture on the left, exploring various technologies, which are the spots in that sea of blue. And as the firms exploit various technologies, the technologies are linked because clearly if you discover the internal combustion engine, the need for people to shoe horses reduces, so the discovery of one technology has an impact on the fitness of another technology, motor engineers on blacksmiths. That's built into the model by modelling the technologies in a fitness landscape. And what you see on the right is the emergence of the growth of GDP. Don't worry about that, that's the general trend, the blue line behind all the squiggly lines. The emergence of a general trend in GDP from these local interactions. Right, I'm now going to try and bring this back to the theme of the talk, which is complexity and causality, but particularly in the context of the meeting, cosmology. This is a very long quote, but the essence of it is to address the question of how do we produce a universe which is such that complexity can emerge. And the author here has two possible suggestions. The first is to consider that complexity, in particular life, is an adaptive process that would have emerged in nearly any kind of universe. This is a tantalizing answer, but our own universe shows that life requires extremely specific conditions to exist. It's hard to imagine life in a universe without chemistry, maybe without bound states, or with other numbers of dimensions. The second idea is to accept the existence of many universes with different laws where we naturally find ourselves in one of those compatible with complexity. Now, what I've tried to argue is that dismissing the first of those two possibilities relies too much on our ideas of perturbative causality and too little on our understanding of how complexity does actually arise. If we look at the special cases and the case that's made for these special values of the parameters, what we ask is, what happens if you perturb just one of these? Let me give you an example. You ask, what happens if you perturb epsilon, the strength of the nuclear interactions? Well, if all you do is perturb epsilon, then you make nuclear interactions either faster or slower. You end up without the spectrum of elements, or if you make the interactions stronger, you have the spectrum of elements and probably more elements to play with, but you make stars very short-lived. Except that you don't, because if you make gravity more important compared to nuclear interactions, then the Kelvin-Helmholtz timescale over which stars will exist without the need for nuclear interactions will be extended. And so you'll have an entirely different type of stellar universe with stars driven by gravity. So there's the possibility of exploring changes in the parameters that are not just perturbative changes at one at a time, and we don't actually know what happens in that big space in between. But we can have a go. We can look to string theory, which tells us that there are many possible ground states to the universe, or to the string theory universe. There are multiple fields with their interaction. So we have the condition under which there are multiple agents interacting with interactions of various strengths. In that situation, it's conceivable that the majority of universes living in the middle of that diagram actually contain the conditions for the evolution of complexity. The second point that I want to make, just to emphasize this, is that if we lived in a situation where we knew only of the sun was the only star we knew about, then we'd look at the value of radiation pressure to gas pressure in the sun, and we'd think it's amazing that that is so fine-tuned as to create a habitable zone. In fact, beta isn't tuned at all. All values of beta occur in stars, from 0 to 1, because stars aren't produced singly. Stars are produced in collections of stars with a range of masses, with a range of beta parameters, and of course we happen to live round the ones that have an appropriate value of beta. So, if I can come to a conclusion, if you talk to development biologists, they will tell you that physicists are far too limited in their imagination as to how complexity can arise. They're quite happy that you throw things together, enough agents, enough interactions, complexity arises from interacting agents, you will get complex systems emerging. Of course, physicists look at the fine-tuning of numbers to get rather precise results. So I think the message is that we should perhaps consider more strongly the case that complexity can emerge in a range of conditions in almost any universe or set of universes that we might have, and that we might argue that the physicists should take a line out of the biologist's book and become a little bit more sloppy. Thank you.
Thank you very much for your interesting lecture. We have some time for a discussion. Are there some questions, comments? Please.
Okay, thank you very much for your talk. I'm not sure I understand your last argument about the sun. Because you say, okay, you observe the sun and this beta should be 10 to the minus 2. This is an observation. It doesn't mean that it is a fine-tuning. To be a fine-tuning, you would need a theory of stellar objects and see that something that, if you change this parameter, this phenomenon of having a habitable zone is not possible, which is another issue, that observing that the sun is beta equal 10 to the minus 2. So I think when we talk about fine-tuning in theoretical physics, we have a theoretical framework that we believe is a good framework. Of course, it has limits in what it can explain. And in this framework, you have these fundamental constants, and you can play with them, and you can ask yourself, when do a phenomena stops to be active when I change this parameter? And you mentioned the constraint on this nuclear rate, but you say, okay, we vary this epsilon, but we can vary also gravity. And I agree with you that what was done like 20 years ago, but now people they know more about nuclear physics and gravity. So if you believe that nature is described by general relativity and the standard model, you can go to your star and vary all the constants simultaneously. And in this higher dimensional space, which is 26 dimensions for all the constants, you can try to plot the zone in this theoretical framework. So this is dependent on your description of nature, where you have to be for stars, or let's say for a specific question like, I want stars to form carbon. Is it possible or not in this parameter space? And there you can ask yourself whether there is a fine-tuning. Even though the main problem is that you don't know anything, but you don't have any measure in this space of fundamental constants. So basically, fine-tuning is a very intuitive thing. So it's not clear to me that this notion of fine-tuning is so well addressed actually in this understanding of physics. And can you just clarify the point of the sun example?
Yes, in a sense, what I'm imagining with the sun example is a situation in which we have much less theoretical knowledge than you're positing, than we do in fact have. So just imagine where we don't have that theoretical knowledge yet, the sun is our only example of a star. What we would then believe that we have a fine-tuning problem. We then go on to understand stellar structure, which is the analog of understanding string theory and multiple vacua and so on. And then when we understand it in the context of stellar structure, you're absolutely right, we'd see that beta isn't a fine-tuning problem. And what I'm trying to do is take that analogy to thinking of the tuning in the context of we now have string theory, and that's our idea of the universes that we might have.
So to summarize our point that we have some numbers, we have a set of numbers, and we have to ask which relation between these numbers are fine-tuning and which one are coincidences. Is that what you want to? Okay.
Yes, yes.
Are there some other questions? Okay.
Yeah. It seems to me that it might be a good thing to sort of try to specify what is needed in order for complexity to occur. And it seems to me that one thing, like if you take the early universe, one thing that you really need is what you might call a process of differentiation, right? I mean, if you, a process of differentiation and a stabilization of what differentiates, because then as soon as you get that sort of thing, then you can begin to get a complexity developing. But if you just get things that don't differentiate, you get a universe in which there's no differentiation, and in which what differentiates is overwhelmed so much by the chaos that it doesn't stabilize, then you're not going to get complexity. Would you agree, or?
Well, you may know more about this than I do, but my view would be that what I've been trying to argue is we don't have a general theory, but let's look at some examples. And in many of these examples, it doesn't matter what parameters you throw at the system. You have agents which are interacting, enough agents interacting in a diverse number of ways.
Right.
And lo and behold, these emergent properties emerge.
Right. No, I agree. I guess what I'm looking at is sort of what you might call a lower or a more fundamental set of characteristics which are needed for this to happen. Okay.
Some other questions? If not, thank you once again for your lecture.